d phi, that is my dz, into P of epsilon into e to the I phi by Q of epsilon into e to the I phi into logarithm of epsilon into e to the I phi. So this is equal to we do not know what is I to 0. So it will be something like this will be some constant. This I have to evaluate in the limit epsilon tending to 0. So this one is kind of constant. That is like P of 0 by Q of 0, which will be some constants, and this logarithm of epsilon. So I think the argument is that this epsilon comes out and you have in the limit epsilon tending to 0, this whole thing will become 0. So that is like limit epsilon tending to 0 and e to the I phi d phi into this quantity will be P of 0 r. So let me put it as P of epsilon into the I phi by Q of epsilon into the I phi into logarithm of epsilon plus I. Now this term will be something like a constant P of 0 divided by Q of 0, and you have two terms. One is limit epsilon logarithm of epsilon as epsilon goes to 0, and this is one limit, and the other one is anyway epsilon into I phi, so this epsilon goes to 0. So this also epsilon logarithm of epsilon will go to 0 as epsilon. Is that correct? Yeah, I think this. So it will go to 0 in this. So there is no contribution from this, there is no contribution from this. So we have these two contributions. From there we can get this. Another general result, just someone asked me during the tea time. Okay, this is just reminds me that someone asked me at the tea time that if you have a rational function like this, we have suppose p of x divided by q of x. We have a rational function, and supposing you, okay, let me call this as rational. So let f of z be equal to p of z divided by q of z. Some rational function, and let's say z equal to z naught is is a pole, a simple pole, and g of z naught, sorry, p of z naught is not 0. If p of z naught is not 0 and g of z equal to z naught is a simple pole, that means q of z naught is 0, but p of z naught is not 0. In which case, we can write down p of z as, expand this as p of z naught plus z minus z naught into dp by p prime of z naught, and so on. And then write q of z as q of z naught plus z minus z 0 into p prime, q prime of z naught plus so on. Now we know that q of z naught is 0, so this is equal to z minus z naught into q prime of z naught plus the other term. So what we'll have, if I write f of z, I can write this as p of z naught plus z minus z naught into p prime of z naught plus so on, divided by z minus z naught into q prime of z naught plus so on. Now, if I want to find out what is the residue of z at z naught, then I will write this as z minus z naught, or if you can consider this as kind of, okay, let me put it this way, z minus z naught into f of z naught. The limit is that f of z in the limit z tending to z naught. So these you will have z minus z naught into p of z naught plus z minus z naught into p prime of z naught, etc., divided by, I can write down z minus z naught. I pull out and write this as q prime of z naught plus the next term will be, I pulled out z minus z naught, so it will be z minus z naught by factorial 2 into q double prime of z naught and so on. Now this will cancel here, and if I take the limit z tending to z naught, what I will have all these terms will go away, all these terms will go away. So what I will have is p of z naught divided by q prime of. So this is in general for any rational function, residue at z equal to z naught is p of z naught divided by q prime of z. So the question was asked during the tea time in the context that we had this f of z in the morning as e power a z divided by e power z plus 1, right? So I had expanded this around z equal to I pi to get the residue. But if you use this, it is basically, if this is your p of z and this is your q of z, so you can write this as, according to that, e power a I pi, that is p of z naught, divided by e to the the derivative of this is e power z, e to the power I phi. E to the I phi is minus 1, so it is minus e to the I phi. So you can get this directly from this general result. So, let me consider one physical problem which gives rise to an equation that is. So, let me consider this problem of force oscillator. When we talk about a forced oscillator in one dimension, we will have an equation of motion like this: x double dot plus omega naught square x is equal to some f of x. This is the force term, and this is the natural frequency of your oscillator. Natural frequency of your oscillator. Huh? Yeah, I don't have damping right now, but let me consider an undamped force oscillator. Yeah? But who prevents me to force it? I can still force it. It's not damping also, I can force it. Right? So, I want to introduce a quantity now, which we will probably do a little later in some future workshops in detail. So, I want to replace this force with an impulse force. That means this is a force as a function of time, but I will use right hand side as a delta function, t minus t prime. Delta function, this is a Dirac delta function, which means it area under this function is 1 if you include your range of integration t prime. Then the solution of this equation with this kind of a force on the right hand side is generally called the Green's function. So g double dot plus omega naught square into g. So g will depend now on t and t prime, and this is called Green's function. So essentially what we have to do is we solve this equation, then get Green's function, then our x of t can now be written as integral g of t prime into f of t prime dt. So I can get x of t, I don't have to solve this problem. If I solve this problem and get g, then I can put it in the integral and get x of t. This is easy to understand if I write this equation as some differential operator L operating on x is equal to f of t, and now if I put L on this, so this means what? This implies L operating on g is delta of t minus t. Now if I write L operating on x here is equal to integral L operating on g, it does not operate on f because it is only operating on variable t, into f of t prime dt prime, that is equal to L operating on g is delta t minus t prime into f of t prime dt prime, which is equal to f of t. So which is the given equation. So this way of writing is consistent with the given problem. So our aim is to solve So we have to solve g double dash g double dot plus omega square g is equal to delta of g minus. Now I can define this g of T prime as, okay, so I can define this as integral minus infinity to plus infinity from g tilde, okay, so g tilde of some omega, which will be Fourier transform of this into e power I omega t into d omega divided by t. I am just defining. I can always define g t t prime in this fashion. Essentially what I am trying to say is I will take that as a linear combination of all the plane waves, and plane waves, this factor e to the I omega t has a weight. I am just calling that as a weight. And you can write down delta of t minus t prime as integral minus infinity to infinity e to the power minus I omega t prime into e power I omega t d omega by t. So this becomes the weight, or this becomes the Fourier transform of delta t minus. So if I substitute this in this equation, remember this is the second derivative with respect to time, so it will act only on this quantity. So substituting that, I will get I omega and I omega minus omega square. This is omega naught. So I will have omega naught square minus omega square into g tilde of omega integral minus infinity to infinity d omega by 2 pi is equal to integral minus infinity to infinity e to the minus I omega t prime, this approximates the I omega t e to the I omega t d omega. So you can see this factor and this factor is there at both sides, integral. So if you equate the integrand, you can immediately see that g tilde of omega is equal to e to the minus I omega t prime divided by omega naught square minus omega naught square minus. Yeah? This one? I am substituting this in this equation. And I take integrands. So essentially I have got Fourier transform of the Green's function. So I take the inverse Fourier transform, I will get the Green's. Now when I have to take the inverse Fourier transform, I know I have to substitute that g omega here, that's all. So g of t prime is equal to 1 over 2 pi integral minus infinity to infinity e to the I omega t minus t prime divided by omega naught square minus omega square d omega. So I have to just integrate this. But when I am integrating this, I will have a difficulty that we have encountered when we integrated one of the previous integrals. When we talked about e to the power ix by x, because this has poles on the real line. And if I have to integrate using a complex plane, if the real line has one of its arm of the contour, then I will have the same difficulty. So if I consider a complex omega plane, okay, so if I want to write this integral minus infinity to infinity e to the power I omega, okay, so t minus t prime is, I will call it as some tau, divided by omega naught square minus omega square d omega. If I take a contour integral of complex plane, then I have omega naught is real, because there is a natural frequency of the system. So at plus omega naught and minus omega naught, we have poles. So if I take a contour like this, then there is a plus omega naught and a minus omega naught. So we have poles on the real axis. So when I take a contour like this, what I have to do is I must come here and then go around this, and then come here and go around to solve this integral. Minus omega naught, you make a detour. But what does it physically mean? It physically means that at this point, you are giving a slight imaginary part to this root. So what you are doing is that on your path, you are assuming there is some slight imaginary part. How do I get this slight imaginary part? I can get this provided I solve this equation, that is g double dot plus some eta into g dot plus omega naught square into g is equal to delta of t minus t prime. If I solve this problem by introducing some damping, this damping provides this necessary imaginary part to get over this. Essentially, physically, whatever small detour that we are taking around a real part, in this physical example, we can interpret it as introducing a small damping. So you can see here, this will be something like omega naught square plus I eta omega minus omega square into g tilde is equal to e power minus I omega t prime. So essentially this equation g of t prime will be 1 over 2 pi integral minus infinity to infinity e to the power I omega t minus t prime divided by omega naught square plus I eta omega minus omega du. So this is what will happen if you have a small damping, and you can write this denominator. What are the roots of this denominator? So you can write omega square minus I eta omega minus omega naught square is equal to 0. then you can write this as omega is equal to I eta plus minus square root of I square eta square minus I square eta square, so minus eta square plus 4 omega by 2. So you will have I eta by 2 plus minus square root of omega naught square minus, or if I pull out that omega also, so 2 omega naught square root of 1 minus eta by 2 omega naught whole square divided by 2, and this will get cancelled away. So you can write 2 roots omega plus is equal to I eta by 2, and whatever this is, if eta is small, this is real quantity. So I will call this as eta plus I omega, and omega minus is equal to I eta by 2 minus omega, where this omega is equal to square root of 1 minus eta by 2 omega. Now you can see that if eta is equal to 0, so omega naught. If eta is equal to 0, then omega is omega naught. If eta is not 0, it will be slightly less than omega naught, but it will also pick up an imaginary part. So that means if you have eta equal to 0, it is minus omega naught, and before minus omega naught, it will pick up an imaginary part and then take a detour. Similarly, just before I omega naught, just before plus omega naught, you pick up a detour, and then so it is because of the presence of this eta, you have a complex roots, and you can. Okay, so this is just to give you a physical meaning of taking this detour, and you can solve this problem in the same way. Like if you are including this, you calculate the residue. If you are excluding this, you forget about that singularity. Huh? You can exclude both. You can include both.
So how will you invert the second
Huh?
You are inverting the second flow.
Yeah. This you are asking? Yeah. So you can actually include this. It all depends upon how we are taking. For example, if I start with 0 here, when I come here, the phase is pi. Now pi to again 0. Okay, pi to 0, and now I have, it is like pi, and then pi to 0, then this is 0, and then 0 to pi, and pi again. So it depends on how you are measuring the phase. So let's say this is pi. So now it is pi. Then this is going from pi to 0, right? Pi to 0. This is 0. Then this is going from 0 to, this is like 0 here. Then this is going from 0 to pi. This way, that means pi to 0. Already this is 0. So I take this, and this goes from 0 to pi, and when I should finally get back to 0 at this point, right? So I must have that consideration. So that's how I have to choose which one to be included. But I think it doesn't matter. You can include both, you can exclude both. I think your results will not change. There are four possibilities, include both, exclude one, and you have to take care of those limits. That's all. Okay, so this Green's function can be calculated, and once you know this, then you can write down the final result in terms of integral g of dt prime f of t prime. This is a very general technique of solving inhomogeneous equations using Green's function. This is inhomogeneous because there is a right hand side for the differential equation which is non-zero, which depends on t. So such equations are called inhomogeneous differential equations, and they can be solved using this Green's function. There is also another example where we have this Green's function technique used. Of course, finally the complex analysis part of it is same as what we have discussed here, but physical context in which it is appearing is somewhat different. But in general, for Helmholtz equation, this becomes any other function f of r. It turns out in Schrodinger equation, for scattering you will have psi of r. So this kind of a problem, or Laplace equation for the Poisson's equation, this is called Helmholtz. Or Poisson's equation. What is Poisson's equation? Del square phi of r, scalar potential, is equal to minus rho of r. Now, if you write down, for example, Poisson's equation, if you write down del square g of r prime as minus delta of r minus r prime, delta function, and you can show by again using the same trick of Fourier transform, you can show that g of r prime is equal to 1 by r minus r. Have 1 over 4 pi. This you can read out actually if you write down the Coulomb's law. Potential at r is given by 1 over 4 pi epsilon naught integral rho at r prime divided by r minus r prime d3. Now, if you compare, so this is, if I compare, this is equal to integral g of r prime into, if I compare the right hand side as minus rho of r prime by epsilon naught, this is my right hand side, d3 r prime. If I compare these two equations, we get g of r prime has to be minus 1 over 4 pi into 1 by modulus of r minus. Then you will write this as simply del of r. If I put a minus sign here, I will get a plus sign. That's it. I am not solving this, I am just reading out from the Coulomb's law. But you can solve this and get the same answer. Solving this requires, again, same kind of Fourier transform techniques. For example, okay, maybe I will just leave it here because more of, I will solve more of Poisson equation than it requires to get the final result where I will use contour integration. So maybe I will show it once. That if you have to do this Poisson equation, so this is the equation that I have to solve, then I will define g of r prime as integral d3k by 2 pi the whole cube whole power 3 by 2. That is because whole cube will write it cube into g tilde of k, that is the Fourier transform of this, into e to the power I k dot r. This is the Fourier transform of this. And similarly, delta of r minus r prime will be written as integral d3k by 2 pi the cube into e to the power minus I k dot r prime into e to the power I k dot r. So if I substitute that in this equation, you can see that this del square will act only on this one, you will get minus k. So I will have essentially all the integral transforms, Green's function, everything. Integral transforms, if you see, all differential equations can be converted into algebraic. And here we will get an algebraic equation for the Fourier transform of the Green's function. So we will get minus k square into g tilde of k is equal to e to the minus I k dot r. So g tilde of k, we get it as minus e to the minus I k dot r divided by k square. So if I substitute it in this equation, I will have g of r prime is equal to 1 over 2 pi the whole cube integral minus sign e to the minus I k dot r divided by k square into e to the, that is my g tilde k, into e to the power I k dot r dot r into r prime. So this is equal to minus 1 over 2 pi the whole cube into integral e to the I k dot r minus r prime divided by k square. So you can actually choose your, without any loss of generality, you can choose your direction of k along the z axis. You choose k along z axis without any loss of generality. Then this becomes minus 1 over 2 pi the whole cube into integral e to the minus I. So this dot product will be the cos theta. So e to the power I k modulus k into modulus of r minus r prime into cos theta.